In this video, we will be covering the topic of Newton's method. Newton's method requires knowledge of derivatives, continuous functions, and roots, or zeros, of functions, as well as the ability to perform algebraic manipulations. We will begin by discussing what Newton's method is and why we might use it. Afterwards, we will demonstrate the fundamental ideas used in developing Newton's method. Then we will dive into the derivation of Newton's method formula and work one example. To finish, we will discuss instances when Newton's method fails and the various ways we might correct those failures. What is Newton's method? Newton's method is an iterative process used to find the roots of functions. It was developed by Sir Isaac Newton and Joseph Raphson in the 1600s. Newton was the first to write about it, but he did not publish his works until after Joseph Raphson, around 1670. Why use Newton's method? Primarily, we use Newton's method to find the roots of polynomials and other functions whose derivatives are easy to compute. In particular, we use Newton's method to find the roots of degree 3 or higher polynomials, since the closed form solutions are either extremely tedious, or for the case of degree 5 and higher, no general closed form solutions exist. Newton's method is also useful because of its quick convergence once a point near the root is reached. We will illustrate this property later. We will now demonstrate the fundamental ideas needed to understand Newton's method. Here is a graph of an exponential function shifted down 1 unit. Now, a single point on the graph is selected. In this instance, we pick the point whose x value is 2. Next, we create a straight line, whose slope is the same as the graph at that point, and which touches it at that point. This is known as a tangent line. We now look at where the line intersects the x-axis and we give it a label 2. Notice that this point is closer to the root than the original point was. Watch what happens as the starting point we pick moves. As you can see, the closer our starting point in orange is to the 0, the closer the resulting point in blue is to the 0 as well. Now we look at a new graph. This graph will be used again later when we do the mathematics more rigorously. This function is a cubic function, meaning it is a polynomial of degree 3. Similar to before, we start with a point hopefully near a 0. In this case, we pick the point whose x value is 0. Next, we construct its tangent line. Again, we look at where this orange tangent touches the x-axis. Now we're going to do something a little different than before. Instead of sliding the starting point around, we're going to apply the function to that blue point. Here you can see that the pink line shows us where this value is. The reason we're doing this is because when we use the mathematics later, we'll not be able to see the graph, and so we need to rely on the property that those blue points move closer to the root each time we repeat this process. Now we select a new point to build a tangent line for. Notice where the tangent line intersects the x-axis is much closer than before. Let's zoom in to see a little better what's going on. As you can see, the point is fairly close to the function 0, but we aren't satisfied yet. So we'll do this process again. Follow the pink line up to the function and make that point our new orange point. We will build its tangent line and then zoom in again to see just how close we're getting. One last time, we follow the pink line and make a tangent line at the resulting point. Here the graphing program has reached its limit for accuracy, and so we've successfully found the root up to 4 decimal digits of accuracy. We start with the most important part of our derivation, which is a formula for the tangent line of a function at some point k. There's not enough time in this video to explain where it comes from, but that can be found in other resources. Here, f prime of k denotes the derivative of f evaluated at k. Next, we pick a starting point, just like we did on the graph. We call this point x0. Here, we want the tangent line to be at the point x0, which is why we're replacing k by x0. Now, we need to find a way to determine where this line crosses the x-axis. To do this, recall that the x-axis is where the y-axis is constantly 0. So to find this point x, we need our line to have the output of 0, which is why we're setting g of x equal to 0. Next, we do some algebra and subtract f of x0 from both sides. Then we need to divide f prime of x0 to further isolate the x. Lastly, we add x0 to both sides, and for convenience, we flip the equation so x is on the left. Recall from the example that this point x becomes the x component for the new point that we find the tangent line of. This means we've reached the end of one cycle of this process. Let's rename the x to x1 since we started at the point x0, and now we've moved to a new point x1. If we repeat this process over and over again, we want a formula that incorporates the property that if we start at x0, we get an x1, and then if we go again, we get an x2, and so forth. If we let the indices on our x's have a counting variable n, we can rewrite the formula like so. Notice that if n is 0, we get the equation just above, but if we let n become 1, then we get the next formula. This type of formula is called an iterating process, since we're taking the output and using it as an input. This is the final form of Newton's method. Next, let's run an example. This example will be the same as the one used in the visualization portion of this video, so feel free to skip back to it and see how the math lines up with the visualization. Here is our function f of x. Our first step is to take its derivative so that we can plug it into our formula. This will give us the following formula. Admittedly, it's not very pretty, but in some instances these formulas can simplify. Now we pick a starting point x0. Here we let it be 0. Note also that x0 corresponds to n being 0. So we evaluate the formula from the previous slide when n equals 0 and x0 equals 0. Notice how all the terms with zeros will reduce since 0 raised to any non-zero power is 0. So we're left with x1 equal to minus 5/3 over minus 1, which becomes 5/3. This is about 1.6 repeating. Now we use this x1 in the formula where n equals 1. This gives us this large expression, which will eventually simplify to 245 over 207. Feel free to check this by hand if you wish. So we have x0, x1, and x2. We can keep repeating this process over and over, but we want to know when to stop. We determine when to stop when we satisfy an accuracy condition. For this example, we want the correct value up to 8 decimal digits. In this table, we see the values for xn given each value of n. The red digits are digits which are not correct. In other words, they do not match the root's actual value. Notice how the number of correct digits in white increases very quickly. After only 5 iterations, we have the desired accuracy, since the difference between x4 and x5 is smaller than our desired accuracy. We now switch over to looking at the ways in which Newton's method can fail and the ways we might be able to fix it. We start with derivative failures. For some functions, the derivative at a point might not exist. This is the graph of a function with a vertical asymptote at x equals 2. When we select a point to start Newton's method, it is possible that the tangent line intersects the x-axis exactly where the asymptote is. This stops Newton's method from working, since the next x value cannot be found. We can fix this problem by shifting our point a little. Before, we were at x equals 4, but now let's try x equals 3.9. You can see that the new point is not at the asymptote, and we get a new x value. As we continue for this graph, we can see Newton's method now works and does approach the 0. We now look at loop failures. In this example, our function is defined everywhere and is differentiable. But let's observe what happens when we pick a starting point far from the 0 there on the left. Here at x equals 0, we get a tangent line that gives the next x value of 1. This new point, however, gives us a tangent line that intersects back with the x-axis at 0, and so we get back to the same point we started with. This is not desirable since we would bounce back and forth between the two values indefinitely, and not converge to the 0 there on the left. To fix this, we need to pick a new starting point that is closer to the root we want. As you can see, now Newton's method will work. Next, let's look at divergence failures. These occur rarely for polynomials, but for other types of functions they can exist too. This is the graph of the cube root function. Let's start with a point very close to the 0. Here we pick x equals to 0.1. We proceed as usual, but notice something curious. After one iteration, the x value is actually farther away than when we started. If we continue, we see that the value keeps getting farther and farther away from the root. In this type of failure, there are no fixes for getting around it, and we would need to use other methods to find the roots. Let's talk about zero-slope failures. This is a graph of the sine function. If we manage to pick a point like this one, observe what happens. See how the new point is directly at the top of the curve? When we make the tangent line to this point, look what happens. Since this tangent line has a slope of 0, clearly it will not intersect the x-axis anywhere, and so our method fails. Mathematically, this occurs when we try to divide by 0, since in the Newton's method formula, the derivative is in the denominator. This means if we require the derivative to be non-zero at the points we pick. To fix this, let's start a little closer to the 0 than last time. It becomes clear now we have no difficulty in getting Newton's method to work properly and converging to the 0. In this video, we covered the derivation and motivation for Newton's method, the mathematics behind the process, and we addressed the ways in which Newton's method can fail and the possible workarounds that exist. Thank you for watching this video.